So with this first example problem, we need to rewrite the equation in logarithmic form. Now, in general, let's say we have some exponential expression, a is equal to b to the c. To rewrite this as a logarithm, remember that logarithms have the same base as our exponential expression, so it would be log base b, and logarithms are always equal to the exponent, so the logarithm will be equal to c. And the input of our logarithm is always what the exponential expression is equal to. So when you have b to the c equals a, you can rewrite this as log base b of a equals c. So this is a little bit abstract, but we can look at specific examples here. So let's just rewrite the original problem. We have that 0.25 is equal to 2 to the minus 2. Now, you can see this is true since we're dividing by 2 twice, so this is really just 1/4, and 0.25 is also 1/4. So it's a true equation, but we want to practice rewriting this as a logarithm. And as a logarithm, this would have the same base as our exponential expression, so log base 2, and the logarithm is equal to the exponent, so minus 2 is what it's equal to. And the input here of our logarithm is whatever our exponential expression is equal to, which you can figure that out by process of elimination once you know the other two. And personally, the way that I always remember how to rewrite this is to start with the fact that the bases are the same in both exponential and logarithmic expressions. And then remembering that logarithms are exponents, and so they are equal to whatever this exponent is. And then by process of elimination, you know that what your exponential expression is equal to must be your input to the logarithm. So this would be the answer to the first part. And in the second one, we're going to do the opposite. We're going to look at this specific logarithm and rewrite it as an exponential equation. So let me just rewrite it. We have log base 8 of 512 is 3, which you can see is true if you think it through, since we're asking ourselves, what do you raise 8 to get 512? And you would raise 8 to the third power. So to rewrite this as an exponential equation, the base is the same, the logarithm is equal to the exponent, and the input of our logarithm is what our expression, our exponential expression, is equal to. So 8 to the third equals 512. That's what we would put right here. So let's keep going. We'll do a couple more problems that are similar but a little bit different. So in this one, we have 4 points that are plotted on the graph y equals b to the x. And you could imagine extending this. This is some exponential equation that shoots up very quickly. That's not the best drawing, but that's essentially what's happening here. And based on just these 4 points, we want to plot 4 corresponding points that have to be on the graph y equals log base b of x. And like I said, we're given y equals b to the x. So remember that these are inverses. They're inverse functions to each other. So if this was f of x, then this equation here would be f inverse of x. And remember that with inverses, they switch x and y. So if the point, actually let's just start looking at these. So if the point 0, 1 is on this graph, then our logarithm would have the inverse to that. It would be at the point 1, 0. And actually we need a little bit of room, so let me just draw this over here. So that's at the point 0, 1, and we really need to know all of these since we're going to switch all of them. This looks to be at 1, 3. This one right here looks to be at 2, 9, and this point right here is at the point that looks to be 3, 27. And you might recognize this is really just the equation y equals 3 to the x. But we don't need to know that. That's just something you can tell with practice. So on our inverse function, we're going to switch x and y. So let's do all of that in a slightly different color. Let's go with a blue. And so y equals log base b of x. We just switch these points. So 1 comma 0 should be on our graph, since we just switched 0 comma 1. And 3 comma 1 will be on our graph. So 3, let me delete that. 3 comma 1, that's right there. We'll also do 9 comma 2. So 9 up to 2, right about there. And on the Khan Academy, this interactive grapher will plot the points exactly, so you don't have to be too precise here. So 9 comma 2, and then 27 comma 3 will be our last point. So 27 here, and then all the way up at 3. So that's that point right there. And you can see the logarithm, which would look something like this, is very slow growing, since it's the inverse of our exponential function, which is very quickly growing. And of course, since you do know what y is equal to, since it's y equals 3 to the x, this is really y equals log base 3 of x. But again, we don't need to know that. We just need to be able to plot these points. So if you see a problem like this, the general idea is just to switch the x and the y values when you understand that exponential and logarithmic functions are in fact inverses of each other. So let's do one more problem. Again, it's slightly different. This time we're dealing with a table rather than a graph. But it's the exact same strategy as the problem before. That if this is our function, so this is our f of x, then this graph here, notice, is the inverse function. Now they use g of x because they don't want to explicitly tell you how to do these problems. But when you find the inverse of b to the x equals y, and you go through the process of switching x and y, you would get log base b of x. So this right here, this is actually our inverse function. That is equal to g of x in this case. So to solve this problem, we just need to recognize that inverse functions switch the x and the y values. Like notice for f, it goes through the point, let me use a lighter blue. So it's going to go through the point 0.792 comma 3, and our inverse function, this function right here, we can highlight that in yellow just to make this a little bit more explicit. This inverse function goes through this point switched. So it goes through 3 and then 0.792. So the key recognition here is that we just switch the points from one table to the next. And notice in this box right here, we'll come back to this one, that this has an x value of 10, and we need to find its y value. So let's look at our original function, where when x is equal to 1.661, we get a y value of 10. So the inverse function is going to switch that. Instead of y being equal to 10, now x is equal to 10. And instead of x equaling 1.661, y is now 1.661 for our inverse function. So up here, we can put this 1.661 into the box. And likewise, we'll do the same for this point. We essentially just need to find 7 down in this table, since we switch y for x here. So in the original function, we have some x value, which gives us a y value of 7. Then for our inverse function, it goes through an x value of 7, and its y value is this 1.404. So that means this x value for our original function must also be 1.404, so that these 2 points line up just like these 2 points and these 2 points did. So in our box up here, this is just 1.404.